All right, so we can get started. Welcome everyone. Welcome to Spring 2013 ISAR Colloquial Series. I'm thrilled that our first speaker is our new affiliate member in the Institute, and he was willing to give the first seminar of this important series. Please make note of this. These seminars are arranged for you. And they're also sponsored by IAI, which is one of our the sponsors, partners of this institute. And so the whole purpose of this informal seminar series is to provide an opportunity for faculty and students to become more familiar with the diverse nature of ISR. And I'm hoping that you all take advantage of this. So our speaker today, Gabriel, is an associate professor in the Civil and Environmental Engineering Department here at the University of Maryland. A full professor. I am very sorry. This is my full professor. That's right. I apologize. That's right. Thank you for correcting me. He also has an appointment in Applied Mathematics, a Statistics and Scientific Computation program in the Civil and Environmental Engineering Department. His group. He's a group coordinator for Civil Systems program, and he's also a co-director of the Master of Engineering and Public Policy program, a joint degree which is between engineering and public policy school. Steve's interests are in optimization and equilibrium modeling and in algorithm development for solving complementarity and two-level problems in engineering economic applications. He has over 25 years of experience in industry and working in the area of the mathematical modeling and analysis. He's a member of the Institute for Operation Research and the Management Sciences, Mathematical Programming Society, NPS, and a senior member of IEEE. In addition, he's also an associate editor for Energy and Operations Research, and is currently area editor for the Energy for Networks and Spatial Economics, and also an associate editor for Energy Economics. So with no further ado, Steve Gabriel. Thank you.
Well, thanks very much for inviting me to give this first talk for the series. It's probably a little bit different than some of you, at least than Ali Reza's, whose talk I heard recently, which we wrote a proposal together, but I only understood a fraction of what the talk was about, but it was still exciting. So hopefully everybody here understands at least that fraction that I understood in this talk. But please feel free to ask if you have any questions. Here's the outline of the talk. First, talking a little bit about optimization and equilibrium problems. Equilibrium is a very specific meaning that I'm going to give you very shortly. And there's a connection between optimization and equilibrium. Sometimes you can get an equilibrium problem from optimization. Sometimes the other way around. Sometimes you can't. But the thing that sticks it together are these so-called Karush-Kuhn-Tucker conditions, which if you're about 45 years old or older, you know them as Kuhn-Tucker conditions. I won't ask you to raise your hand to reveal your age, but if you're under 45, then they're Karush-Kuhn-Tucker. And the reason is, Kuhn and Tucker are two very famous mathematicians. Kuhn is still alive. I saw him recently at a conference. But they invented this theory about optimization problems in the 50s. Turned out in 1938, there was a student at, I think, University of Chicago, Karush, who basically invented it. So they gave him credit for it. So if you're a master's student here at ISR, there's many things you can do, like having your first initial as part of a theory. So don't think you can't accomplish great things. Anyway, KKT conditions is the connection between these, as we'll see. And equilibrium problems have many names, but the name I'll use here is complementarity, which is sort of a generalization of linear programs, game theory, problems in engineering and economics. It's got a whole list of things. And then I'll focus a little bit more on an energy network equilibrium, and then at the end talk about some results that we have with EDF in Paris. EDF is the French national energy company, and two of my students who are working on the project are here, Sexton and Jacob. You can raise your hands. So we apply an actual equilibrium model to generate things about energy markets that people are really interested in. So several governments have used this model, and so it's not just academics who are interested. Here are some books for those of you who are interested. The field started roughly about 1960s, equilibrium modeling, that is, maybe a little bit before that. We have a book that just came out, number 7 there, in case you're interested. And plus, there's many other books related to game theory and optimization that are relevant as well. Anyway, I like to see the big picture first. So what is the big picture? Well, if you're an optimization person or have interacted with optimization models, you know about linear programs, that's LP. You know about quadratic programs, that's the middle circle. And I guess I'll use this. And then integer linear programs. So in my opinion, the left-hand side, these are the easy problems. Convex programs are easy to solve relatively. And the more interesting ones and harder to solve are on the right because they involve some sort of non-convexity in the problem. Many engineering problems are non-convex. If you look at things like Kirchhoff laws or Weymouth equation for flow in the pipeline, they don't have a nice convex nature to them. And as such, they're harder to solve, but you have to approximate them somehow. Anyway, the left-hand side are sort of more standard problems. The right-hand side is harder problems, but there's been a lot of research in them. That's the big picture. And then there's the bigger picture. You know, how does complementarity and equilibrium fit into this? Well, complementarity problems are also another version, slightly more general, called variational inequalities, is the biggest circle. Inside that is linear programming. So every linear program is a special case of this class of problems I'm about to tell you about, as are quadratic programming problems, like a portfolio optimization is an example of a quadratic programming problem. All nonlinear programs, via their Karush-Kuhn-Tucker conditions, are also special cases. Integer programs, things that are non-convex, are out here, though. And there's a whole slew of other problems that have no one optimization. They can be a Nash-Cournot game where there's 2 or more players competing against each other. They can be the so-called traffic equilibrium, where you're trying to figure out how people choose their routes. And if everybody's shifting every day, you know, because it's quicker to take this route than that route, if everybody's sort of optimizing for their own travel time or, you know, minimizing their disutility, then what is it going to be like in equilibrium? And this involves not only engineering, you know, road traffic, but human behavior. So it's a good mix of sort of psychology, economics, engineering, all thrown in. That's the so-called traffic equilibrium problem. There are problems in mechanical engineering, structural engineering, contact problems. Something does something or it doesn't. There's sort of a bifurcation going on. All these are non-optimization based problems that are also examples of complementarity, as I'll explain. So this talk is a little bit tutorial as well as some results. So for the tutorial part, let's consider a nonlinear program. Some of you are familiar with these. We have an objective function. We have a bunch of inequality and equality constraints. And we want to find an x that satisfies at the same time all of these constraints and does the best job in minimizing f of x. So this is pretty standard. People have looked at this for, you know, several hundred years at least. And what's new and exciting about this is, you know, some of the theory in terms of the algorithms to solve these problems, as well as their connection to this larger class of problems called equilibrium problems. So for those of you that knew about convexity and forgot about it, or people who never even heard about convexity before, this is the picture you want to keep in your head. So we like to have convex functions, and here's an example of a convex function, which the definition says you sample it at 2 points, x1 and x2. You take a weighted combination where the weights sum up to 1, and it turns out that the function, when you take the weights outside, is actually always bigger. That's the chord. So the chord is always above the line. And in optimization and equilibrium modeling, by extension, we always want convex functions if we can. It's much easier for various reasons. The other thing that's important are what are called convex sets, which basically says you take any 2 points and any convex or weighted combination joining those 2 points, so any line segment between them is also in the set. So if you like food, I like food a lot. Donuts are not convex. Hamburgers are convex. And, you know, you can go on from there. So here's a little in-class homework because, you know, professors have to always give out homeworks, right? So which of the following are convex sets? Yes? Of course. No. No, because you can go from 2 points in the set and the line segment connecting them is not. Triangles are convex. This is a little trickier. If you have the set of points that satisfy this inequality, where this is a convex function, is that a convex set? And so I know Sexton knows this. Yes or no?
Yes.
Yes, okay. If it's not a convex function, it may not work. And then this is like the linear programming feasible region. That's also a convex set. So certain feasible regions to problems are convex, some are not. Depends on the application, but you would like to have that. Here's the result that, this is well-known result, why convex programs minimizing a convex function subject to convex feasible region are important. Any local solution are automatically global. So but basically what that means is you solve it with GAMS, and you get a solution. You know it's not just some local solution, but it's the true global solution, or one of them if there's many. And that's why we like convex programs, why we try and convexify in many cases because of this result and other results. The thing that sort of puts everything together are these Karush-Kuhn-Tucker conditions. And what they basically say is, if you're trying to solve this problem under certain convexity assumptions, you can just solve these conditions, which look like a mess the first time you've ever seen them. But it turns out they're not really a mess. You know, if you got rid of the g and the h and you looked at this first condition, you would basically say the gradient of the objective function vanishes. That's pretty well known. You learned that the first day of calculus. But in fact, we have these constraints we have to take care of. And we got little multipliers, u's and v's, multiplied by them. And so what this really says is the gradient of the Lagrangian function vanishes. So some of you are familiar with the Lagrangian function. And then the really interesting part comes up right here. Basically, if I have a point x that's feasible, meaning it satisfies the g's and the h constraints, in addition, for each of these constraints, I have multipliers, u's or v's. But for the inequalities, I have this so-called complementarity, which means that the slack in this constraint times the multiplier has to be 0. Okay, so what does that mean? That means basically if there's any amount of resource left in here, that's what this is usually referring to, then the corresponding price for that resource has to be 0 because of complementarity. So if you haven't used up to your limit, how much would you pay for one more unit? You'd pay 0. Conversely, if the price of that unit is positive, it must mean you've used up the entire resource. And so there's a lot of economics behind here, and I'm giving the 12-second tour of economics and complementarity, but you kind of get the idea that the multipliers play some role. And so this set of conditions is something you're trying to solve for. It's basically finding x's, u's, and v's that satisfy this equation, these inequalities, and the complementarity, and any h's that equal 0. So this is a system you're trying to solve for.
That's a local result, and you don't need convexity, correct?
You need convexity for sufficiency. You need constraint qualification for the other way around.
The way it was stated, you don't need convexity, you need differentiability, and it's a local result only. If you want to put convexity, then you use the
Then you get global. Yes, exactly. I didn't say that, but I think that's coming up on the next slides. As usual, you're like 2 slides ahead. What?
You need strong duality.
Well, you don't have strong duality for nonlinear programs all the time. So for linear, you do. There's a duality gap. But basically, yeah, you need, if f is convex, the g written in this form is convex, and h is affine, then these are sufficient.
And there's a very nice geometric interpretation of that equation, which basically says the gradient of the cost function is collinear with the gradients of the
Yes.
constraints.
Yeah, it's the negative gradient is in the cone that's spanned by these things. Yeah, that's like another lecture, though. So. Okay, so here's a small little example. What does it mean to solve those KKT conditions? This is a small problem. It's got everything linear. We keep everything happy. Keeping everything linear reminds me, I was a graduate student at Stanford. I had George Dantzig as my master's advisor. Some of you know George Dantzig. He's the father of linear programming. I saw him maybe 7 minutes the entire year. And outside his door, he had a little picture of, I think it was Linus, the one with the blanket. And he's like sucking his thumb, and it says, happiness is assuming things are linear. So I'm going to assume things are linear here. Anyway, if you look at the KKT conditions, we take the gradient of f, we take the gradients of these constraints, and we got the multipliers. We try and solve this system. We got the inequalities and the complementarity, the g times the u's, and so on. We have 4 cases if you wanted to do it by hand, based on the u's being positive or 0, so 2 times 2. So you could solve this by hand. This would be a very big waste of your time, unless you have to do it for class, let's say. But essentially, it's solving a system where you're looking at different cases, And so that's one way to consider this. And as was pointed out, John pointed out, there's a geometric interpretation to at least that first thing where the Lagrangian derivative vanishes. It basically says the negative of the gradient of the objective function, so this blue line, is in the cone that's spanned by the gradients of the active constraints, these two constraints I had. So you can see that directly here. And what are the weights? The weights are the multipliers. And then there's a whole bunch of theory relating to tangent cones and inner product cones and things like that. But there's a lot of geometry involved. Okay. And the big theorem, I'm going to get to complementarity soon, but this is sort of the lead up. The big theorem says if f and g and h are C1, and they have these properties, namely convexity, then these conditions are sufficient. You solve the KKT, you solve the original optimization problem. And so you think, okay, that's the end of the story. No, not really. And here's an example to clarify this. Whoops, here's an example to clarify this. So here's two disks. They intersect only at the point 1, 0. So this is the easy problem where you say, what's the optimal solution to a feasible region that has 1 point? Well, it is that 1 point. But if you try to solve the KKT conditions here, they're not solvable. There are no way to solve for those multipliers. It's like, wait a minute, how's that possible? We got a linear objective function. I'm assuming things are linear here. I got convex, these are actually convex constraints. So what's the problem? Why can't I apply the previous theorem? Well, the reason is the feasible region doesn't have the right shape, the so-called constraint qualification. There's only 1 point. And even though you have all the conditions you need for the sufficiency direction, if you're at a solution, like at the point 1, 0, they're not necessarily satisfied. So they're not necessary. Turns out to show the necessity direction, you need a lot more. And this is what you need. If you're at a solution that's local solution, then you need the so-called constraint qualification, like linear constraints, linear independence of the binding gradient constraints, or there's a whole slew of these things. And so they're not exactly the same thing. For linear programs, these KKT conditions are necessary and sufficient, but once you move away from the happy linear world, things are not so nice. Okay, that was a slight introduction to nonlinear programming, which normally takes like 3 lectures, so just to let you know. What are complementarity problems? Well, they generalize what I just talked about for KKT. And they have the following very simple, deceptively simple form. There's basically 3 conditions. So I'm given a function f that's from Rn to itself. Want to find an x such that f of x is non-negative. The x's are non-negative. And there's complementarity between the two. So each component wise equals 0. Remember the complementarity in the KKT, the g's times the u's. So this is the generalization. So here's a simple example. Suppose I have R2 to R2, this function, which first component is minus x1 plus x2, second is this one. So these are the conditions I want to find. Find an x1 and x2 that make the first 2 components of f non-negative, x's are non-negative, and then f1 times x1 is 0, f2 times x2 is 0. So 0, 3 you can just say is a solution because you just check it. Are there any other solutions? Okay, you 2 guys in the back, you can't answer this. Or 3 people, sorry. Are there any other solutions to this system of inequalities and equations? So I'll let you think about that while you're drinking your coffee and doing whatever else you're doing, checking your email or what have you. But try and find another solution. You can graph it. What you can do is you can graph these 4 things and then try and interpret the complementarity in terms of being on a line or not being on a line. And I will take answers up till midnight tonight, in case you're interested. That's the pure complementarity problem. And it looks like no connection at all to optimization. But in fact, this complementarity thing is sort of like a hint. It's related to KKT. Here's a slightly more general version, which people use more often, which is, again, the same sort of conditions. I have a function that goes from Rn to Rn, but now I've got 2 sets of vectors, x's and y's. And the x's satisfy this pure complementarity form, namely the associated function is non-negative, the x's are non-negative and complementarity. And then the y's are associated with just equations. So basically you have a mixture of equations and free variables, these guys, or you can see it here. And then I have a bunch of inequalities for the functions, and then their corresponding x's and the complementarity. So here's another system. It's a 3 by 3 system, but you're trying to find x's and y's that satisfy that, and I gave you one solution here.
This two-dimensional problem you can solve them by
You can solve it graphically or by hand.
plotting, okay, and this
Right.
is really what I call a high school problem.
It's a high school problem, but a really advanced high school.
I teach this and I tell them it's a high school problem into my undergraduate system engineering class.
Okay, I'll give you a 5 by 5, and then we'll talk.
5 by 5 I cannot visualize.
Yeah, you can't visualize. Anyway, for the first time you've seen complementarity, it's nice to visualize
That
it.
is 2 by 2, I can put all
Yeah, yeah.
even 3 by 3 will come difficult.
Well, I can guarantee you there's no PhD student of mine that for his thesis solved a 2 by 2, and
No?
solved it as the thesis. Yeah. In fact, I'm going to give you a gas model equilibrium at the end. That's about how many variables? 60,000? 66,000. So that's a little bit harder.
Well, our system engineering students doing 1 million by 1 million.
Okay, well, we'll get there one day. Okay.
I'm going to teach you.
No, that's okay. So now I talked about KKT conditions. I talked about complementarity. How do they meet? Well, they meet because let's look at KKT's system again. Even if you've never seen that before today, just look at it now for the first time then. So basically we got a set of equations, some corresponding variables, they're the x's actually. I got some inequalities like greater than or equal to after I multiply by -1 here, it'll be greater than or equal to. Corresponding variables are non-negative, and then the product of those things are 0. That's complementarity. And then I got a bunch of other equations with free variables. So this is exactly in the form of a mixed complementarity problem. And here it is. So the mixed complementarity problem that corresponds to KKT conditions has 3 sets of variables, x's, u's, and v's. And it takes on this form. And we're at the same time trying to solve this complementarity system. And so what this means is that every nonlinear program, if it has KKT conditions that are valid, is a special case of mixed complementarity. And you might say, wow, big deal. What does it do for me? Well, what it does for you, as we'll see in some examples, is at the same time, you're solving for the primal variables and the multipliers, the Lagrange multipliers. So you can manipulate those multipliers, which typically in energy models, as I'll talk about in a little bit, are prices. So what if the players see the prices and can manipulate them, as in game theoretically, then that gets a much richer model, and it has all kinds of feedback. In traffic modeling, if you look at the so-called, I guess they call them Lexus lanes. These are the lanes that you have to pay money on to reduce the travel time. There's an actual real name, I forgot. Is it HOT? Yeah, HOT lanes, I think. And we have them, we sort of have them for the ICC, I think, right? I know in Virginia, yeah.
Virginia called Virginia I-495.
Yeah, yeah, and I think also like Singapore has some of them, and Southern California.
It stands for high occupancy city lanes.
Yeah, yeah. So there, I call them Lexus lanes because you have to be able to afford them or something. But anyway, if you see the price, which changes, dynamically, that'll change how many people take a particular route, which then changes the prices again, and you want to simultaneously solve for that. And models like this, where you're at the same time looking at the flows, that would be the x's, and the travel costs or the prices, do that very well. But anyway, this slide basically says KKT is a special case of complementarity. And there's some advantages and disadvantages in doing it. In our book, we talk about...
Actually, I have a question. Do
Sure.
you know of any system with these hot lanes that the prices have rapidly changed?
I thought in Singapore they have it, but we have some transportation specialists
In
here.
London and here and in California, when I checked, they're fixed.
They're fixed? You had some?
Yeah, based on that.
Traffic flow, they're flow-dependent prices.
Yeah, I don't think they're implemented
Yeah.
yet.
Because that would be a good idea.
Yeah.
If you want to.
That would be a great research idea. And I was starting some research about 5 years ago or 10 years.
California, they have the data
Yeah.
that they collected from the environment, and they could do that.
Well, you could also have environmentally friendly versions of that where you're having to internalize the negative externalities of pollution. And if you had to pay for that with an easy pass or whatever it was, does that change your routes? It does. It would. So you can basically get feedback with these models, which you couldn't with a straight optimization, because you compute the multipliers after the fact and they don't get fed back. It's like a catch-22 or something. Okay. And how are these things connected? Well, this is the so-called principle of symmetry or principle of integrability that says if I start with an optimization problem and I take the KKT conditions, I will, of course, get a complementarity. But I can go the other way as long as this function f is, its Jacobian is symmetric. Why? Because it would relate to the Hessian matrix of this function, and the Hessian is always symmetric. That's a necessary and sufficient result. And here's the formula. You just integrate something. And it tells you, oh, here's how I can start with complementarity and find an appropriate optimization problem, like the inverse problem that relates to it. And in the 80s, this was pretty important because a lot of people were doing traffic equilibrium modeling and other things where they didn't have solvers to solve complementarity problems. They had to rely on optimization. So they always converted things that way. But now we have solvers for complementarity. OK, now let me talk more about energy and give you a little inkling as to an idea what's going on. So I have, it was a 4-hour talk, right? No, I have till 5, right? 5, OK. So imagine that there's a market with 2 producers. This also works with any number of producers greater than 2. And you'd want to take into account that they may have some sort of market power whereby they can withhold their production to manipulate prices, to make the prices higher. And the first question you might ask is, well, wait a minute, they're producing less, so they'll make less money, right? So why would they ever want to do that? And the answer is no, they're not necessarily making less money because the price goes up and the quantity goes down, but maybe the price goes up more. And we have seen this in practice in the natural gas markets. You have Russia, which is a huge supplier of gas, that had a dispute with Ukraine in 2006 and in 2009. So it should have been 2012, but I guess they missed that year. And basically, they were withholding the quantity flowing through Ukraine, which then went to Western Europe as a downstream customer, because they had a price dispute. And there are other indications in the US of pricing problems. No company will ever say, yes, we manipulated the market. They will just pay the fee, because otherwise then it would be billions of dollars. But imagine, if you will, there's 2 producers. They each produce Q1 and Q2. And this is the inverse demand function, which is the price as a function of the market quantity. And we're going to assume everything is linear here just to keep it happy. So this is the intercept. This is the slope. So they see this, but they can manipulate the price by changing, like if you're producer 1, by changing Q1. They can't control Q2. Somebody else is controlling Q2, and it's exogenous to them. And again, keeping things easy and simple, let's assume their cost function is just linear, which in electric power is not accurate. It's piecewise linear, if anything, when you have different generators that come online. Or in some cases, it's not even convex. But anyway, this is simple. And so what does the appropriate optimization problem look like for each player? Well, each player has roughly the same optimization problem, just different variables. And what they're trying to do is maximize the price from the market times their quantity minus their cost, subject to non-negative quantities. Of course, they could have much more elaborate constraint sets in terms of ramping up, the so-called unit commitment problem, all kinds of fancy stuff. But for our purposes, this is fine. It turns out if beta is positive, so it's a slope that's strictly, well, with the minus sign is strictly negative, then this is a convex program, and you can take the KKT conditions, and they're both necessary and sufficient in this case for different reasons. And the KKT conditions are just taking the derivative of everything that we needed here, is that this function is non-negative, the quantity you're trying to solve for is non-negative, and the complementarity. That's producer 1. Producer 2, it's the same thing, except they're solving for Q2. And what you can do is you can concatenate these 2 sets of conditions. You just stack them one on top of each other. And it's now, instead of a 1-variable complementarity problem, it's a 2-variable one. You're solving at the same time for both producers. And you're trying to find the solution to the complementarity problem that has this particular F. It's a very specific F. Of course, you could just keep concatenating 100 producers. And you can have a model that has 100 different energy producers trying to do what's best in their own interests, the so-called Nash approach. and manipulating market prices and all that. And what is the eventual price? How many, in our world gas model, how many producers do we have, roughly? We have like 40 nodes, roughly, right? So maybe we have like 100 and something if you multiply by the 3 types of producers. We have like 120 of these producers in our model. And much more elaborate engineering equations than just non-negativity. But basically, this example is to show that you can put multiple optimization problems together and you get the solution of them simultaneously when you do complementarity. And the idea here is this guy, producer 1, takes Q2 as fixed because the other player is deciding that, but decides Q1. Player 2 takes Q1 as fixed and decides Q2. But you put all their optimality conditions, these 2 things together, and you get this more general complementarity problem.
How feasible is this when some of the relationships to some of the engineering parameters are nonlinear?
Nonlinear is fine as long as you can take the KKT conditions, and you may have to approximate it. Like in Kirchhoff laws, they use DC load flow models. But if you put in the full sines and cosines and all that, it won't work, because then you don't have KKT conditions.
Does your model take into account where the producers are located?
Yes.
Where the demand is?
Yeah, and that's a really interesting point, because we've solved variations on this where you have like a 2-level model with a leader that decides prices, a dominant player or something. And they actually make prices lower in some nodes because the overall profit and the congestion effects that they induce give them more profit. So it gives slightly non-counterintuitive results, but that are correct. So that's like the interesting models that do that, right?
I wonder if you've tried to verify these predictions that come out of these models versus what happens in reality in real markets.
Yeah. Well, we're working with real clients, Department of Energy, in EDF in Paris, and then in Norway, and they seem to like it. And have we sat down and said, did we get this price? No, we do that first, actually. We calibrate all the models to history. When I say we, I mean the 2 guys in the back, basically. And yeah, so we do first do that, and then it's a sort of a what-if approach. What if this pipeline, was disrupted? What would the prices be? What could the prices be? It's counterfactual. So we sort of do what you're saying, but
What happens when you have dynamics?
like a dynamic game?
Yeah, in other words, if you are a smart grid, okay, what's going to happen is, first of all, you have price variation and demand variation and generation variation during the day,
Right.
but also depending on what people do.
Yes.
So then it becomes, the dimensions become humongous, right?
Right. You have to make some simplifying assumptions.
You cannot do the simple thing that we do use utilization. You string out the vectors indexed by the time, and then you solve a huge problem.
Well, you can do Bender's decomposition and things like that for these. I have some papers on that for complementarity problems. So you can separate the things that make it solvable in parallel, for example. You can do that. People have done that. Let me give I think it's one more example, and then go to some actual results for that study we did. This is a small little power plant or power distribution model. It assumes that there's an independent system operator who's managing things, not individual players competing against themselves, but someone who's looking at cost minimization for the system. No engineering here, just to keep it simple. No loop flows, no line losses, no other engineering details. And this is actually the very famous and well-known transportation problem that a lot of you know about, where you have a bunch of supply points and demand points, and these are the costs. So if you ship 1 megawatt across this line here, it's going to cost 10, and 5 over here, and so on. And as the independent system operator would like to do, they'd like to minimize the overall cost of meeting the demand over here and not exceeding the supply you have over here. And this is a well-known problem in operations research. It has a certain unimodularity property for the coefficient matrix. So you get integer solutions, which is fantastic because you don't have to solve it as an integer program, but it just works out that way with integer data, that is. Anyway, so if you solve that particular problem, I believe this is the correct answer. You get these flows on the arcs. So like power plant 1 sends 10 units to demand unit 3, but nothing to these other 2. These values on the nodes, these are the prices that you'd get by solving the transportation problem, like linear programming problem. And it says the price over here is, supply price is 0, 3, demand price is 9, 5, and 4. And there's something very interesting going on with the transportation problem, which we're generalizing when we talk about complementarity. And I'll show you in just a sec. Basically, all the optimality conditions, well, some of the optimality conditions, have this sort of thing going on, which says the transportation cost, Cij, from going I to j, plus the dual price at the supply price has to be greater than or equal to the price at demand in equilibrium or at optimality. What that says is, from an economic point of view, the price you buy it at or you produce it at, plus the price to get it to the destination market, has to be greater than or equal to the price you can sell it for. Otherwise, there's going to be incentive to keep changing. And in particular, if there's any positive flow, this has to hold as an equality. So in economics, this is the marginal cost, marginal benefit thing going on. And you say, well, that's great, but I can't manipulate those prices. Those are just given to me after I solve it in GAMS or wherever package I use. So how do I generalize that? And this is where complementarity comes in. Complementarity says you take that same relationship, but now I have supply curves and demand curves. These are inverse. So this is supply price as a function of how much you supply, demand price as a function of demand. And supply should be upward sloping, demand should be downward. And these are just examples. And what if, instead of just saying, here's the price after the fact, if the model understood that there's a dynamic between how much supply or demand you had and the resulting price? Wouldn't that be interesting? And in fact, these are the optimality conditions. Well, maybe optimality, but they're an extension of optimality, going from what we had for transportation to this new problem. It's called, by the way, the spatial price equilibrium, where it says the price that you get, but as a function of supply is the sum of everything leaving that node, plus the transportation cost has to be greater than or equal to the demand price, and demand is everything coming into the node. And then this sort of relationship here that says, if you have positive flow, this has to hold at equality, or else there's really no incentive. In some cases with this principle of symmetry, you can go back and find the optimization problem that relates to this. But if these functions are not symmetric, related to Jacobians being symmetric rather, you can't. And so this is a problem for which there exists maybe no optimization. And in fact, this is an example of a complementarity problem, a pure complementarity problem. Because what does it say? It says this function, Cij plus the supply price minus the demand, is always greater than or equal to 0. The corresponding flows are always non-negative. And the third thing you need is complementarity. But this basically right here, this implication is complementarity. It says Xij times this function here has to always equal 0. Because if the x's are positive, then this thing equals 0. Basically, this thing equals 0. And if this thing is strictly positive, it means there's no flow. So complementarity is an if-then rule as well. And this problem was looked at in the 1950s by Samuelson and others. So it's been around for a while. They just didn't have the software until early 1990s to solve it.
Do you need symmetry actually?
You need symmetry in a certain part to get the optimization problem that could have had its KKT conditions being that.
Because in several problems, the Cij will be a direct graph actually.
Yeah, but it'll work out that you can solve an optimization problem whose KKT conditions are this only under symmetry. Otherwise, you can't, and it's just can't set it up that way.
You can't say that means you cannot go through the optimization path.
You can't go through the optimization, yeah.
But you can solve it by other methods if Cij is directed.
Yeah, you could do things around it. I'm just saying the theory doesn't allow you to find an equivalent inverse problem, basically. Okay, so that was that problem. Here's a small problem from our book. This is very typical of energy markets. It could also be anything that's delivered. But basically, you have this small little make-believe world. You have two nodes. And over here, you have two producers, A and B. Over here, you have producers C and D. The producers over here, they decide via some optimization problem how much to produce and how much to send, the flow, from 1 to 2. Over here, they just produce. They don't send back. So this could be a power network. It could be a gas network. It could be anything that you're shipping and producing. And what is driving everything? Well, it's that you have demand at each of these nodes. And then you have these prices, pi 1 and pi 2, which should be endogenously determined to accurately measure how the system values each of those goods. And then lastly, you have some sort of coordinator, which in power is the independent system operator. In other systems, it's somebody else, but I call it the network operator, who decides G. And G is their version of flow versus the F's, which are the producer's versions of the flows. And you'd like them to be the same. But there's a cost. And so here's typically an optimization problem. This is without market power for the producer. And almost all producers are the same. They just have different variables or they don't have flows. But basically it says, for producer A, who's at node 1, how much should I sell times the price I get at node 1, that's your revenue, plus how much should I ship to node 2 times the price at node 2, so this whole thing is revenue, minus the cost of production, minus the cost of transporting, subject to some consistency type things. And in fact, in natural gas networks, or power networks, I should say, there may be a regulated component to the tariff and then an endogenous part, like a congestion fee. You know, this is what you declare that you have to pay because of cost recovery mechanisms, and this is because the pipeline or the power line is congested. So it's a exogenous factor for this player, but somebody else determines it somewhere in the model. So this problem, assuming the C's are convex, is a convex program, and you can take the KKT conditions, which are these. Okay, we don't really care, but they're basically the same, almost the same for producers A, B, C, and D. So you have 4 KKT conditions. You also have market clearing equations with associated prices. These are the demand equations and supply equations that say basically the total sales in node 1 has to equal the demand, and then there's a price associated with it. And then the total amount available in node 2, which includes flows from node 1, has to equal demand. So again, we got equations and free variables. Plus we got the 4 KKT system for the 4 producers. Then we have the market network operator problem, which is this is their tariff times the amount of flow that they allow minus their costs, subject to flow being not above capacity. You know, and they get to maybe decide, should I increase the diameter of the pipeline or add extra transmission lines, or if it's a water network, add more capacity. This is some optimization problem as well, and so therefore it has KKT conditions if we assume that C is convex. So those are those. There's a market clearing for the capacity market. So the G is what this guy determines, the F is what the producers determine, and the corresponding price is tau, the congestion price. Okay, so now we have 4 producers KKT, we have the network operators KKT, we have 3 sets of market clearing, 2 for the nodal and 1 for the capacity market. You put all that together, it's also a complementarity problem, because it's a mixture of equations and inequalities with complementarity. All right, so that's just examples, and there's many, many more examples that you could look at. Here's a real thing that we presented, I guess it was May 30th. And we have several governments that have been interested in this world gas model that we have, in part because it has this very nice feedback with various producers having some measure of market power, or maybe there's no market power for some other producers, and it takes into account also the network effects and so on. And what's very popular or very hot topic these days in the US at least is shale gas. You've probably heard about it in the news. And in particular, this talk was a little bit about this. China has the most shale gas reserves, but there's a huge amount of uncertainty. We gave a talk to in China about this, and they were quite interested because they want to know, how will their coming into the market change prices in Europe? Will they make their money? Will the U.S. get involved? And the U.S. recently is getting involved with LNG markets. LNG is liquefied natural gas. And here are the main questions. So the effect of Chinese natural gas prices on European gas market, because you can ship gas, if you liquefy it, it's down to about minus 260 Fahrenheit, and you can put it in a boat and take it anywhere pretty much. And sort of like, how does the US enter into this picture as well? That's another question people wanted to answer. So we have this world gas model we've developed over the last 10 years or so. It's been used in a bunch of studies, like for Statistics Norway, which is a branch of the Norwegian government, about possible cartels in gas, like you have for OPEC. There's a thing called GasPEC. Well, people talk about it like that. Effect on U.S. shale gas for the Department of Energy. Some more Norwegian stuff. You know, why Norway? Because they're a very big producer of gas in Europe. And we wanted to look at sort of the influence of China and carbon policies and so on. So here's schematically what our model looks like. It's for every country, and we have 40 nodes, roughly a country. Sometimes it's 2 countries. Sometimes, like the US, it's 4 nodes, I think, right? No, sorry, Russia's 4 nodes, right? In any event, it has the whole supply chain for gas. It has producers. It has their marketing arms who trade the gas to other countries, maybe. It has pipeline operators, storage operators, and consumers. And each of these, except for consumers, is solving optimization problem, KKT conditions, plus we have market clearing. So each of these is like one complementarity problem, and then for each node, we repeat it. And it covers about 95% of the worldwide consumption. Actually, it did a few years ago. We haven't updated that number, so I don't know. Maybe it's a little bit off, but it's a lot. It goes up to 2050. We decide investments, operation levels, whole bunch of things. We allow market power. We have seasonality of demand. Anyway, it's a very large-scale complementarity model, about 66,000 variables, solves pretty quickly. We haven't tried to parallelize it, but that would be a really neat thing to do. We have several directions that are sort of funding-oriented. You know, client wants to see this, then we do that. Or NSF wants to see this, we do that. Anyway, here's, oh, these pictures are not coming out somehow. Imagine there's a map of the world here. This is the United States, clearly, and there's 3 places we're exporting gas to, from the West Coast, the East Coast in Maryland, actually, and then the Gulf of Mexico. And they can either go to South Korea, India, UK, or Spain. And this is a kind of politically tinged thing, because why would you want to export this natural resource? Well, you get more jobs if the industry gets better, but the prices go up because then you're selling your gas to someone else, and the price domestically goes up. But there's some motivation on the demand side and the supply side for, you know, having exports of U.S. gas. There's a huge amount. At one point, it was 100 years worth of gas if you include this new shale gas. And like Japan will pay any price. They have no natural resources. They depend on natural gas a lot, even more after Fukushima. And so very interested potential customers, or ready customers, I guess, and very somewhat interested supplier. So that usually makes for a market. And here's a schematic of all the shale gas only that we have in the US. And just in the Marcellus Shale, roughly where we are, it's about 11,000 billion cubic meters, which in the US, we do about 600 billion cubic meters per year. So just in this one area, just for shale gas, we have roughly 20 years of supply in the US. And there's huge amounts, except there's now some environmental concerns.
Is the extraction cost the same in all the geographical areas, or it depends?
No, it's heterogeneous. It depends on many things, basically. Let me just kind of skip ahead because we're coming close to the end. We looked at 3 cases of exporting. Currently, there's 21 BCM that has been approved for export through DOE. If everything pending, it would be about 100 BCM, and then sort of pie in the sky, 123. And mostly, this is just to show you the types of things that we can determine with this large-scale complementarity. So we have by country, but I've grouped it here by region just to keep it simple. You can show under these different cases, and it doesn't really matter what the cases are, but what will the prices be in that particular country or region, all the way from $11 to $11.60 to $11.10. You can show it by year. We can endogenously determine all these prices that people want to know, because essentially it determines whether or not they invest. Academically, it's very interesting because these are large-scale implementations, and you need to do interesting stuff to get it to solve correctly. But places like Spain and UK, where they were the direct recipients of the US gas, the prices dropped precipitously. Like in Spain, $1.50 out of maybe $10, which will change the economy dramatically. And Spain has a lot of LNG import terminals. They're close to Algeria, where there's a lot of gas. And so, they're set up for either pipelines or boats to get the gas. The other interesting thing I think you can see from the schematic, if you look at Spain, so these are the different cases. We just concentrate on these. In 2030, I guess, you can see under the most extreme case of exporting, the U.S. has about 3/4 of the market share of gas in Spain, or maybe 50%. So these are huge economic implications if we start supplying that much to Spain. In other studies we've done, we have a paper just out recently, submitted rather, which shows competition between the U.S. and Russia. Russia supplying pipeline gas, we're supplying LNG gas, and they're displacing each other. So you get these very interesting and non-intuitive and hard to calculate effects with these complementarity models. For the UK, you also show a very big amount of market share for the US, 40% or 28%.
Sorry,
Yes.
Can you inject in this model things like tax policy and
Yes.
also rule-based policies where I have agreements with certain organizations which will make your complementarity conditions actually mixed nonlinear integer programming complementarity?
It may make them. Actually, we have some
You
paper.
have the difficulty of how you're going to handle the hybrid nature of the variables and the conditions.
Yeah, well, basically there are ways around that. We have some other papers where we mix inequality and complementarity, and you basically solve a multi-objective problem. You're trying to minimize the deviation from both. And I'm writing this week an NSF proposal about that.
Because this comes closer to where you have, because sometimes it's not just the pure market conditions,
No.
but there are other things that come from politics, from...
Oh yeah, yeah. Well, some of those you can do by putting in exogenous amounts, like you made an agreement on this. Other times there's if-then logic, and you need binary variables. And then the whole notion of what does this price mean? It's not a convex program anymore, and you have to use uplifts and things like that. Yeah, so very active and interesting area. We've done some work on that, and not many people have done that. And if you look at Japan and South Korea, we group them together, I guess. The US is a big player there as well. So what does this say? Well, this says, let me summarize because we're just about out of time. Complementarity problems are very flexible. They generalize optimization problems via KKT. You can do 2 or more optimizations at the same time. That was the duopoly 2-producer model I showed you. A lot of game theory is basically connected to complementarity theory. There's problems for which there's no explicit optimization, like traffic flow. Each driver is minimizing their disutility, you could say, but there's no explicit one. It's just a set of conditions. It includes zero funding problems. Maybe not obvious to you guys, but it includes that. But probably the most important thing is it allows you simultaneously to handle the primal, like the flow variables or production, and the prices, or the dual or Lagrange multipliers, and have feedback to the players in your little system that can see these prices and can change their behavior to adjust the prices. You can also combine econometrics and optimization. There's a very famous model called the Pies model from the 1970s, which they're using the grandfather or the grandson version of it now, I guess, at DOE. You can look at stochastic versions of complementarity models. What if each producer is facing an uncertain demand curve? How would they hedge? And then you put all that together. It's a very large-scale complementarity, and you can use benders. We've done some stuff on that. And then if you like complementarity, but you think it's too easy, there are these other problems which are not so easy, like quasi-variational equality problems, which generalize VIs, which generalize complementarity, but are related to so-called generalized Nash problems. 2-level problems, either where you have multiple players at the top and multiple players at the bottom, and you have to simultaneously solve for both levels. And so there's sort of like no end to all these classes of problems. And anyway, I just wanted to give you a little brief overview of the type of things that we work on. So thank you.
Thank you. Okay, we have time for a few questions.
So many years ago, with Lee Blankenship and other people here, we looked at quasi-variation inequalities for anything from unit commitment scheduling to actually larger scale problems. Very interesting work. The question is this: we only found interest for utility companies from Electricité de France because they had appropriately trained mathematicians to understand this and work with us.
They have a very good amount of mathematicians there,
They
yeah.
actually do the work and used in Brazil and other places. So the question is this, and you may take the fifth, right? What is your assessment of the technical competency in the utility companies in the U.S. to work with us in these problems, right? Because is it still not very high or what?
I'm being taped, by the way, so just to let you know.
It's interesting to me that you put Electricité de France there
Yeah.
and not, Pepco or somebody else, which is the same problem we had.
Well, I prefer to go to Paris than go to take the metro. Let's put it that
I'm not
way.
asking the question, and I understand.
No, basically, I think what happens with EDF is, and other European companies, is they sponsor PhDs, and I actually supervise one at EDF there. And so they have a real research focus. A lot of European companies, I think, are like that. US companies are more short-term profit-oriented, and so why should they do that when they could take the same amount of energy, no pun, and just devote it to, doing something more profitable? So I think EDF in particular, they're the French national company. They have, a fair amount of money coming in. They want to put it in a place that, gives return on their investment, and they do it with research. I'd be very happy if Pepco would like to do this. One of my students is working at Pepco, actually. He's the spy there right now. And
What Electricité de France does, at least because I still communicate with them, is they actually see revenue coming for providing management systems for national, networks and so on and so forth. And they essentially sell their services and the systems as consultants to other countries.
right.
Who does that in the U.S.?
Well, consulting companies do.
But not the
No, it's too competitive. There they're a monopoly, essentially. They're not monopoly, but a near monopoly. And so they have, they have more cash flow.
So when we educate, sorry for the sequence of questions, but when we educate people toward these very useful and sophisticated techniques, all right, who hires them here?
Here, well, besides universities, you mean?
Right.
Okay, so like think tanks at NIST, they would definitely like things like this.
What about consulting companies like
For companies,
mine?
Definitely consult. I worked in consulting for a number of years, and they love this sort of stuff up to a point. If you can prove that you get a better result, so the client will be happy, yes, they like that. If you're just doing it for the sake of doing it, no, you need to be in a university for that. Whoops. No, seriously though, the bottom line is very important.
No, because why I'm asking that? Because in ISR since the beginning we are very much interested in long-term collaboration with industry and so on and so forth. And in this area, we always have this question.
Yeah, well, I think it depends on the company. There are some U.S. companies that are probably they like the long-term view, and there's some that couldn't care less about the long-term view. And it's not true that every European country cares about the long-term view, but my experience is that more of them do.
I guess a lot of companies, so they hire them, Comet hires them, Exelon hires them, SNC hires them.
Yeah.
There are tons of companies that hires them.
Yeah.
Tons of companies? I wouldn't go there. Because I know the situation very well in Germany, Sweden, Austria, and France.
Yeah.
And there are actually power utility companies, in addition to Electricité de France, who are not monopolies, that they would take people like that because they're interested in doing this very sophisticated analysis.
Actually, let me just follow up with one thing. One of the groups we work with is in Cologne. It's an energy institute. They have 2 or 3 huge energy companies that pay them. And so I think a similar thing here could happen. If you have 2 or 3 or 4 anchor clients, that it's a cash flow thing. So there is hope.
But it sounds like in Europe it's more integrated.
It's actually a very interesting article in Scientific American
Yeah.
that talks about that. But I have another question technically. If I wanted to take this formulation, okay,
Yeah.
and do that sort of what I was asking before, and you can pick your time scale that you're comfortable with, the time varying, finite horizon, but I have time variation.
Yeah. Million variables or whatever.
Is it still doable, you think?
Yes. But that's where you got to get into parallelization, and you have to get into sparsity preserving things. And some of the work we did in the stochastic version of this, we had to do that. We solved up to 250,000 variables. And when you use benders, it was like 7% of the time or something. So yeah, there's no free lunch. You have to do some work. So
How often are solutions unique?
it's a really good question. for like this applied work, we have no idea. Probably locally unique, meaning you adjust the data a little bit and you're not going to get a different answer, but they're not significantly unique, I think. This is also one of my graduate students who mentioned this, because maybe the sum of the market quantity is the same, but how you get it might be different. Like x1 plus x2 is always 10, but maybe the x1 and x2 vary. In that small little network problem I gave you, that's non-unique for sure. But it's not appreciably non-unique in the sense that you still get the same prices. Those are unique. So you need stronger theory to say when there's a solution that's unique. It has to do with things called like strong monotonicity, and these are generalizations of the scalar valued strong convexity and things like that. So I would say rarely in practice do you check that because it's just way too hard. You have to check the Hessian or the eigenvalues of something. For a million variable system, that's not usually doable. But you can try different values and see numerically sometimes.
Okay, as you probably heard, in the last few years, there's been a lot of attention to alternate projection methods, right?
Yeah.
Primarily initiated by Stephen Boyle at Stanford to solve these prime dual problems in a very good way, even distributed, even under distributivity and asynchrony conditions. And some of this looks promising. Is there any motivation or justification to try something like that, meaning distributed and asynchronous, for a problem of this type?
Oh, definitely, yeah.
Give us some intuition, because you are in the area.
Yeah. Well, basically, I'll take the stochastic version of this, where you have a million scenarios, and you want each producer to maximize expected profit or something like that. Well, if there's a thing called Bender's method and the L-shaped method, some of you know, where you have a master problem that has certain complicating variables that, once they're removed, make the problem separable. So it's a block diagonal, and that's basically what we did and other people have done. So yes, and in fact, one of the colleagues in Norway I work with has a 100-node parallel setup, and we're doing things like that.
The distributed agents here will be just the same company trying to solve the problem in a distributed way, or they can be representing different companies or different consumer organizations?
It depends on how you split it. It could be different scenarios.
But you have cases for either?
No, for parallelization, we've done mostly just on the scenario type thing. You could split it by producer, let's say, but then you want to have as minimal linking between the various nodes. And so if you do it by scenario, that splits perfectly. So,
thank you.
Sure.
Any more questions? Please, last one.
Professor, can you briefly describe what is the difference between the mathematical program with the equilibrium function and the equilibrium program with the equilibrium function?
Sure. So here you have one top-level player, like so-called Stackelberg leader, and then you have some complementarity or other problem at the bottom, and there's a connection between them. This one you have more than one Stackelberg leader. So you can have two dominant companies or two governments or whatever it is. They decide some tax rules or what have you. That affects the market that's below, which then sends the market price back, and there's some sort of interaction. If there's two or more at the top EPEC, which people can't even formulate sometimes, it's so hard, one leader, then it's MPEC.
That means on the up level is the leader and the low level is the follower.
Followers, usually, yeah.
Very nice. Let's thank our speaker one more. Next seminar is going to be the first Wednesday of the month of March. Please mark your calendar. I hope to see you.